In this lesson, you will master the techniques for solving various types of modulus inequalities, both algebraically and graphically. This is a critical topic in the Cambridge IGCSE Additional Mathematics syllabus because it combines your understanding of absolute values with inequality logic, which frequently appears in Paper 1 and Paper 2 to test your precision and analytical skills. Our goals today are to solve linear modulus inequalities, handle inequalities with modulus on both sides, and solve modulus inequalities involving linear and quadratic functions. By the end of this session, you will be able to handle these problems confidently to secure those top marks. Let's start with linear modulus inequalities. These are inequalities of the form k times the modulus of ax plus b is less than or equal to c, or greater than c. To solve these, we use the fundamental definition of the modulus. If the modulus of f of x is less than or equal to c, we solve the compound inequality. Negative c is less than or equal to f of x, which is less than or equal to c. If the modulus of f of x is greater than c, we solve two separate inequalities, f of x is greater than c, or f of x is less than negative c. Essentially, the less than case traps the function between two values, while the greater than case splits the solution into two outer regions. Let's apply this to a specific problem. We want to solve the inequality. 2 times the modulus of x minus 3 is less than or equal to 4. First, we isolate the modulus by dividing both sides by 2. This gives us a simpler form to work with. Since this is a less than or equal to inequality, we use our algebraic rule to trap the expression x minus 3 between negative 2 and positive 2. Finally, we add 3 to every part of the inequality to isolate x. This gives us our final solution. X must be between 1 and 5, inclusive. Visualizing these inequalities helps verify our algebraic work. For the graphical method, we sketch both sides of the inequality as separate functions. In our previous example, the vertex of the V-shape is at 3, 0. The horizontal line y equals 4 intersects this V at x equals 1 and x equals 5. Because the inequality was less than or equal to, we look for the region where the V-shape is below the line. This confirms our solution of x being between 1 and 5. Next, we look at inequalities with a modulus on both sides, such as the modulus of x plus b is less than or equal to the modulus of cx plus d. The most efficient method here is to square both sides. We can do this because the square of a modulus is simply the square of the expression inside. This rule, where the square of the modulus of x equals x squared, allows us to remove the absolute value signs. By squaring, we eliminate the modulus signs entirely and transform the problem into a standard quadratic inequality, which we already know how to solve using factors or the quadratic formula. Let's solve the inequality. The modulus of 2x minus 1 is less than the modulus of x plus 4. We start by squaring both sides to remove the modulus. Expanding the brackets and moving all terms to one side gives us a quadratic inequality. Notice how we subtract x squared, 8x, and 16 from both sides. Dividing by 3 simplifies the expression. We then factorize the quadratic to find our critical values. The roots are negative 1 and 5. Since the coefficient of x squared is positive, the parabola opens upwards. We want the region where the graph is less than 0, that is, below the x-axis. Therefore, x is between negative 1 and 5. Today we are looking at a specific concept in modulus inequalities. When we have a modulus on one side and a linear function on the other, such as the modulus of x plus b is less than or equal to cx plus d, we must be very careful. Squaring can introduce extraneous solutions. This happens if the linear side, cx plus d, is negative. Since a modulus is always non-negative, the inequality cannot be true if the other side is negative. To avoid these errors, we use a piecewise approach by considering two cases based on the definition of the modulus, or we use a graph to find the valid intersection points. This ensures we only include values that actually satisfy the original inequality. Let's solve the inequality. The modulus of x minus 2 is less than or equal to 2x plus 1. We will use the piecewise approach. If the expression inside the modulus is 0 or positive, we just drop the modulus bars. Solving this gives -3 is less than or equal to x, or simply, x is greater than or equal to -3. However, we must satisfy our initial condition that x is greater than or equal to 2. The intersection of these two conditions is x is greater than or equal to 2. If the inside is negative, the modulus negates it. This gives -x plus 2 is less than or equal to 2x plus 1. Rearranging gives 1 is less than or equal to 3x, so x is greater than or equal to 1/3. Combined with our condition that x is less than 2, we get the interval 1/3 is less than or equal to x, which is less than 2. Combining the results from both cases, where x starts at 1/3 and goes up to 2 and then continues from 2 onwards, gives us our final answer. X is greater than or equal to 1/3. Finally, we address quadratic modulus inequalities. These involve expressions like the modulus of a x squared plus bx plus c is greater than d. The graph of a modulus quadratic is a standard parabola where any part below the x-axis is reflected upwards. This creates a W-like shape. To solve the modulus of f of x is greater than d, we split it into 1, f of x is greater than d, and 2, f of x is less than -d. By solving these two separate quadratic inequalities, we find the regions where the curve is above the specified horizontal line. This often results in multiple disjoint intervals for x. Let's solve the inequality. The modulus of x squared minus 4 is greater than 3. Following our rule for greater than inequalities, we create two paths. For the first path, adding 4 gives x squared is greater than 7. Taking the square root gives us two outer regions. X is greater than approximately 2.65 or less than -2.65. For the second path, adding 4 gives x squared is less than 1. This means x must be trapped between -1 and +1. Combining these gives our full solution. X is less than -√7, x is between -1 and 1, or x is greater than √7. If you look at the graph, you can see exactly why this happens. The V-shaped sections on the sides in the middle reflected peak all rise above the line y equals 3, giving us 3 distinct intervals for our solution. Let's look at a typical Cambridge IGCSE style question. Solve the inequality. The modulus of 3x minus 2 is greater than the modulus of x plus 4. Since we have a modulus on both sides, squaring is the most efficient method. It removes the modulus signs immediately. Expand carefully using the identity a minus b squared. Make sure you don't miss the middle terms. Bring all terms to the left side. Notice 9x squared minus x squared gives 8x squared, and -12x minus 8x gives -20x. Dividing by 4 makes the quadratic easier to factorize. We look for factors of 2x squared and -3 that add to -5x. Since the coefficient of x squared is positive, the parabola opens upwards. We want the outer regions where the graph is above the x-axis. Therefore, our final solution is x is less than -0.5, or x is greater than 3. Even top students can lose marks on modulus inequalities if they aren't careful. Here are the most frequent pitfalls to avoid. The greater than case always points away from the center. If you write x is greater than -3, you've included 0, which is definitely not part of the solution. Always check if the non-modulus side could be negative. If it can, use the piecewise method or a graph to be safe. Missing that middle term in the expansion is a classic error that will derail your entire quadratic inequality. Take your time with the algebra. This is a fundamental rule of inequalities that students often forget when rearranging their quadratic or linear terms. To secure full marks in your Add Math exam, keep these strategies in mind. Even if the question doesn't ask for a graph, a quick 10-second sketch of the V-shape or the parabola can prevent you from choosing the wrong region. It acts as a mental safety net. Once you have your final range, pick a number inside that range and plug it back into the original inequality. For example, if your answer is x is greater than 5, test x equals 6. If it doesn't work, you know you've made an algebraic slip. Cambridge examiners look for a clear logical flow, explicitly show the squaring of both sides, or the split into two cases. This ensures that even if you make a small calculation error later, you can still pick up method marks. Check if the original question uses less than or equal to. Students often lose a mark by using the wrong boundary symbol in their final answer. Now it is your turn to practice. Please pause the video and attempt these 3 questions. They increase in difficulty to test your full range of understanding. Easy. Solve the modulus of x plus 4 is less than 7. Medium. Solve the modulus of 3x minus 5 is greater than or equal to the modulus of x plus 1. Hard. Solve the modulus of x squared minus 9 is less than 7. Take your time with the algebra and consider sketching the graphs to check your regions. Once you are finished, press play to see the full solutions. Let us look at the solution for the easy question. For the medium question, we square both sides. Finally, the quadratic inequality involves the range between -7 and 7. Let us go through the solutions to see how you did. For the easy question, we used the compound inequality method. By trapping x plus 4 between -7 and 7, we quickly find the interval. In the medium question, squaring was the best approach. After simplifying and factorizing, we identified the outer regions of the upward opening parabola. The hard question required careful handling of the quadratic. By adding 9, we found that x squared must be between 2 and 16. This resulted in 2 distinct intervals on the number line. To summarize today's lesson, remember these vital points for your exams. Use compound inequalities for less than cases and split inequalities for greater than cases. This fundamental logic ensures you are looking at the correct regions of the number line right from the start. Squaring both sides is the most efficient method when you have a modulus on both sides of the inequality. It quickly eliminates the absolute value signs and allows you to work with standard quadratic techniques. Visualize the modulus as a V shape for linear functions and a W shape for quadratic functions. Understanding the geometry of these functions prevents errors in identifying which parts of the graph satisfy the inequality. Always check for extraneous solutions when a modulus is compared to a linear function, and test values to confirm your final intervals. Testing a single number from your solution set is the fastest way to verify that your algebra was correct.